This sequence of videos is going to go through section 6.3 in Night, and this section of the book is differentiating between mass, gravity, and weight. So that's what I'm going to talk about here. So there's a few goals. The first is to differentiate between these three different terms. In the English language, we might use the three of them almost interchangeably, or in certain situations, two of them might have similar meanings. But in physics, and specifically in my physics class, they're going to have different meanings. So we need to clarify that. And then we're going to talk about how you actually would calculate gravitational force and calculate weight. So I say calculate here, but we're not really going to be working through any of those calculations per se, just understanding where it comes from. And later on in problems, this will reappear and we'll deal with it more explicitly, but for right now, we're just going to try to understand where it comes from. So the learning outcomes here are largely related to problem solving. Again, when we do problems, we might need to be calculating gravitational force or weight, and in that case we need to understand which one we're actually trying to calculate. So that also has to do with communicating, that when you define something to be the mass, that means something. You can't actually mean something different and have other people understand. So understanding the differences between mass, weight, and gravity are a big part of communication, and it will be important that you use those terms correctly in your work in this class. So first, let's start with the one that I think is easiest, mass. So mass is an intrinsic property. If I hand you a ball of clay, that ball of clay has a mass. So I thought about getting into fundamental subatomic particles here and decided against it, but everything in the universe we can define a mass for it. Now, there are certain particles, like photons, that have zero mass, but mass is this intrinsic property. It's something that we can define for things. And how we can think about this being measured is something like a pan balance. Now, this gets a little tricky in that it's saying that in the case of a pan balance, you're comparing two masses, that when they balance, your unknown mass equals your known mass. And you've possibly used a scale like this whenever you've needed to slide little masses back and forth. So pan balances are one type of scale. We frequently use other types of scales that work differently, and we'll talk about those later. But in this case, you're balancing a known and an unknown, and from that, you figure out that the mass of the unknown must equal the mass of the known. Now, the reason that that would happen is that the gravitational forces are the same on both of these, and we'll talk what determines that, but the mass does. Now, one of the reasons that we can use this to talk about specifically mass and not just the force of gravity is that this pan balance is going to work any planet. We can put it on the Earth, we could put it on Mars, we could take it to Europa, we could take it to near the edge of a black hole. It doesn't matter what the gravity is. All that matters is that you have the same gravity on each of this. And in this case, I don't mean specifically the force of gravity, but as long as these are in the same place, like on the same planet, two masses that balance must be equal. Again, this might just seem like a very roundabout way of saying mass is something we define that's really just in relationship to other things. That when 1 kilogram is defined, the kilogram is literally a chunk of metal in a closet somewhere. I'm sure it's very well protected. And by comparing other masses to that kilogram, by putting them on a scale like this, we would say, ah, yes, my known special 1 kilogram mass is the same as this other mass, so therefore we also call this 1 kilogram. Okay, so there's a second way that I would like to explain this that might not be any more clear, and I brought it up in an earlier video, I think back in chapter 1 or 2, and that's the idea of inertial mass. So in this case, this is a different type of scale called an inertial scale. You've probably never used one before, so I have to explain a little bit about how it works. So this end of the inertial scale is held down, fixed in place. This is just a clamp. And then there are these two metal bars that go out, and we have our mass here. So this cylinder here represents my mass. And then what you do is you pull it to the side and you let it go back and forth. It just vibrates, that's all. And you measure the frequency of vibrations. Now, we haven't quite studied oscillations, but you have met frequency and period in talking about circular motion. So this is a little bit different, but it's simply how long does it take for this to effectively go from one side, back, and then back again. Now, the important thing to realize is that this doesn't involve gravity, right? Gravity is acting up and down, but here we're going side to side. So this is completely perpendicular to gravity. The function of this scale does not depend on gravity. What you would do is you would come up with the period, again, the amount of time that it's taking it to go back and forth, and you would figure out what it is for this mass. So you would have, for instance, mass 1 has period 1, and you would then say mass 2 has period 2. And if period 1 equals period 2, then mass 1 equals mass 2. And that just has to do with how these metal bars work, that these metal bars flex back and forth, and the rate at which they flex back and forth, the ease of which they flex back and forth, has to do with what this mass is. So we're not going to do the math out for this, but I just want to point out that this idea of making a measurement and comparing the measurements and saying, okay, these two things have the same mass now, this is a way of doing it without gravity. So you don't have to have gravity to measure mass. So inertial scale.